Hello, I'm Mohammed Arashi, and I'm going to explain about statistical model in linear modeling. Uh, Suppose that you provided with this model, uh, and in regression analysis we call it mean regression. If I use the common notation, let's write it in this way. Uh, we consider this error a component as all the instances that are needed to be included in this model, but we didn't include it. So first of all, the meaning of this disturbance uh, component is something like I could have considered nonlinear expression, but I didn't include in this part. I could have considered feather themes or power themes or dependent relations, but I didn't include. So that's the meaning of it. But then actually we are modeling the expected value of the response. So the linear predictor, which is x beta here, is the connection between the explanatory variables x and the response y. Why we call it mean regression once again? Because we model the mean of the response. So usually we write it in this way, the mean of the response. Okay, in this component, so we are provided with the response, which is of dimension n1, and the expected value of y is equal to the vector eta, and the variance covariance matrix of y is given by sigma square identity matrix. Once again, in usual linear modeling, you assume that p the error component has zero mean and variance covariance something like sigma square identity matrix. We can consider different assumptions for the variance of the error, and then so this E has a random nature. Because of the random nature of E, the right hand side is random, so you explain the random nature of the response by this error component. Okay, coming back to the usual model. So the response has these characteristics, and the expected value of y is given by eta, which we consider xb. Here in my notes, instead of beta, I considered b. X is n by p, is actually a constant matrix with non-elements, so it is not random here, and you're working with fixed effect regression. So the effects here are fixed, they are not random, because we also have random effect model, but here we consider fixed effect model. Or better say, we consider fixed effect mean regression modeling. B is a vector of unknown parameters of dimension p by 1. Okay, we want to this violate the common assumption in for the design X, and we know that if we can get a full rank X, so if the rank of X is equal to P, then you will say, okay, the estimate for B, which is denoted here by B hat, is equal to X prime X inverse X prime Y. So you can easily estimate B, and then the target, which is the estimation of eta, can be easily obtained. But here we assume the design matrix X, or this constant matrix X, is rank deficient. So we assume the rank of X is equal to R, or better say we have R independent columns. which is less than p. Further, and we want, of course, we want to estimate eta. So the target is to find the estimate of eta, and we want to see, in this case, what is the estimate of eta. Furthermore, x column wise can be written in this way: hxi belongs to the Rn, which has dimension n by 1, and therefore the linear model can be written in this way. The elements of B are arbitrary unknown parameters. Now, consider this vector space. Suppose VR is the vector space generated by the columns, but with R columns, because we assume rank of X is equal to R. So it's a vector space, and I use R because of the rank, and it also refers to regression. Interestingly, huh? And Y is a vector here. So we want to see how we can estimate eta. And if you, since VR is generated by the columns of X, so the estimation, which is eta, must be in VR. Therefore, I suspect that XB is in VR, or better say, we want to estimate B such a way that the expected value is in VR. And this is the purpose. We have several examples here to show that, okay, this way we can focus on X. For instance, is forget about this page number here. If Y is vector 4 by 1 by these specifications, which mu is given by alpha, alpha, beta, beta, then you can express the linear model in this way. Indeed, if you multiply, then you will get x beta, and so this x beta or b will give you mu easily. If you do the multiplication, this one with this one, so 1 times alpha plus 0 times beta, which is equal to alpha. Again, 1 times alpha. So this is the first element. The second element of the column vector, 1 times alpha plus 0 times beta, which is equal to alpha. The third element in this column vector, 0 by alpha plus 1 by beta, which is equal to beta. So you see, you will get mu. Another example is this one. If Y is 4 by 1 vector with this specification, we just focus on the mean. Huh? Then you can extract X to be like this and B to be like this in order to get eta. Or better say the mu here. Sorry, it's better to be mu. No, yeah, then it's mu. If you do the multiplication, you will get it easily. Another example: suppose that the elements of Y are independently mu sigma square distributed. It means that each yi has the mean mu and variance equal to sigma square, and they are independent. It means that, or better say, uncorrelated. In this case, you will have a covariance of y equal to sigma square r. The linear model then can be expressed in this way, and you can then easily find the expected value. Remember, here it's a vector n by 1, and here I have a scalar mu 1 by 1. So the resulting is this guy, a vector n by 1. Another example is this one. Suppose y11, y12 up to y1n1 is a random sample from a distribution which the mean is equal to mu1 and variance equal to sigma square, and You also have another independent wrap sample, which you display by y21, y22 up to y21 and 2. From a distribution, the mean is mu2 and the variance equal to sigma squared. These cases are common in statistical learning, which you want to check whether the mean of two samples or two populations are equal to each other or not, in order to analyze the performance of a specific effect. So the linear model can be expressed in this way. I merge these two samples, so better say I augment them. So if I display this guy with a vector y1 and I display this sample with y2, so I have this augmentation here, column wise. So I put all the sample points on top of each other, and then I can write the expected value in this way. You will see here we have n by 2 matrix as our design, specific design. This is the x, and then this is the b, 2 by 1, and we then expect to have the expected value, which we can then easily construct it in this way: mu1 up to mu1, and then mu2, mu2. And it's actually n by 1 column vector for the mean of this y here. Another example, you must suppose that the elements of y are independently given by this formula, and this expression can be used in analysis of variance, which is also you can consider from effect modeling, or better say linear modeling, considering effects. Then you can express the linear model in this way. If I do the multiplication again, I will have a vector n by 1. So you have n by 2 design, which I express it by x, and then the b, the effects. We call it the intercept and the slope of a model, or these fixed effects is a 2 by 1 vector. And if you do the multiplication, then you will have, okay, alpha plus beta x1, alpha plus beta x2, up to alpha plus beta xn. And this is actually expected value of y. Now let's go to least square estimator. Coming back, let me append a page here. Coming back to the initial proposed, the proposed here is to actually do a little bit of estimation for a model. Suppose once again this is VR, the vector space generated by the columns of x. Once again we assume that the rank of x is rank deficient, so the rank is equal to r, which is less than p, and you need to consider projection. Why projection? Let me change the color. If I consider y as a vector here, we understood that, okay, the expected value, which you represented by eta or whatever, must be in VR. And interestingly, the thing which then you will say, okay, how can I actually put y or any form of that, or anything of that, or any characteristic of y onto this space? The first thing that comes to your mind is the projection. You can project y on VR. So we will do projection. Let me change my color. Okay, we do the projection, and this is actually the projection. And you know that this projection is indeed x b hat from the theory of projection matrices. And here, and you know that it is orthogonal to y minus xb hat. It's orthogonal to that. So, and if you have two space, suppose that you have V constructed by VR plus VE, the error space. Sometimes I write the capital E, sometimes I write small e, but this is actually the error space. So we call it regression space, and then the other one, the error space. You see these two are orthogonal to each other, and you can construct the V space, the Vn, better say, as this summation here. And this Y, of course, xb hat then is in VR. And then we can use the sum of the squares in order to estimate B and find B hat. And that is very interesting from the properties of projection matrices. That although Y is not in VR, but you can find something of Y, which you see here is we call it Y hat. According to our linear model, we call it Y hat. This Y hat is in VR if I project it. If I project Y on VR. I must also mention that then since Y minus xb hat is orthogonal to xb hat, so Y minus xb hat is in VR. Sorry, VE, the error space. Remember, VE is the vector space orthogonal to VR. So the dimension, since the dimension of VR, we assume already, is equal to R, the dimension of VE is equal to the dimension of Vn, minus the dimension of VR, so it is equal to n minus R. And that's why when you consider any vector or any linear function, the degrees of freedom is equal to n minus R. And this is very interesting. Okay, now so the least square estimated B hat of the parameter B are those values of parameter which minimize the sum of a square. Oh, this is very interesting. How does this sum from where this sum of square comes? Let's remember the sum of the squares of a linear set. We define sum of square of linear set. So let's consider linear set. Let's consider LR, which are represented by C prime Y for those coefficient vectors C in VR. So the sum of the squares of linear sets LR is the square of the length of the projection Y on VR. This we know already. So if I define the sum of a square, the total sum of a square, this total sum of a square is actually the square length of the projection of Y on V or Vn. You know that I can write the sum of a square as Y prime C prime C generalized inverse C prime Y. But from the fact that I also already pointed that I can see V as VE plus VR and L, the linear set on all columns, or better say constructed by C prime Y, which C is in Vn or V, is also equal to Le plus LR. So I can write this guy as better say S1 plus S2. And the square length of projection on the error space and the square length of a projection on the regression space. And this is what we've written here in what follows. So you will see the sum of a square is given by this formula. And suppose that VE is the vector space orthogonal to VR. Here, in the note, I use small e instead of capital E. When I wrote, I used capital E. We know now why the rank is equal to n minus r. And B hat must be chosen in a way that X B hat is the projection of Y on VR. Remember from this depiction here, it's a schematic representation of what is going on now with the sum of squares. You see, I can find B hat if I consider the projection of Y on VR. Then we can write S squared as I said, S1 plus S2. So this is indeed S1. Better say S1, and this is S2. This we call it the square of error, and this we call it the square of estimate of regression. And if I use the notation, if I represent this xb hat as y hat and xb as y, then you see it is y hat minus y. So it's the error in prediction, and it's the first term is the error in estimation. So coming back, the sum of a square is written by this formula, and then you can represent it by these two. Once again, if you remember from that schematic representation, y minus xb hat is in VE. The error space, and xb hat minus xb is in VR. Therefore, S square is minimum if xb hat is the projection of Y on VR. But now, what if you remember the meaning of projection? How can find a projection? Then it gives this interesting relation which we call them as normal equations. And from this expression, you will then be able to find B hat. So from this explanation, we could understand the meaning of sum of a square, and why I need sum of a square in order to estimate the expected value of y. Remember we started from the fact that the expected value of y is in VR. So we motivated that the projection is needed, and then projection led us to find better B hat or better hat. No difference. I will record the rest in another video to make it short. Thank you.